So here's the setup. So a lot of times with momentum problems, you'll have like a bullet and a block, okay? So in this situation, you're going to have a bullet traveling at an unknown velocity. It has a mass of 15 grams. It's going to hit a block of wood that's on friction of the surface. And the bullet is going to make the block move at 6 meters per second. So when a bullet hits the block, there's three things that can happen. Okay, and that's what I tried to show you all back there. Situation number one, the bullet could hit and bounce back. Okay, so that was like that bouncy polymer. Situation number two, it could just go all the way through the block and exit out the other side. Okay. I really didn't demonstrate that because that would be tough to do without the fact that I would trash my carts. It's like, here, I'm going to shoot the cart with a bullet. Okay, what could possibly go wrong in the school? Your third option is that the bullet becomes embedded in the block and it's a California problem. Okay, so that's how we're going to approach this. So we're going to say that this bullet is going to come in here, it's going to become lodged in the block, and then the block and the bullet are going to move off together. Okay, it becomes a California problem. If it had bounced, the velocity would change sign. It would go from positive to negative or negative to positive. If it went through, it would still maintain a positive velocity, but it just would have slowed down because it would have transferred some of that momentum to the block. So this is going to be a California problem. And again, I'm telling you, momentum problems in and of themselves aren't that difficult. It's when you get into trying to take shortcuts. So in this situation, we're going to have two things. We're going to have the momentum of the bullet plus the momentum of the block is going to equal the new momentum of the bullet plus the new momentum of the block. It all starts the same way. If there were three things, if there was a dart involved, I'd have the momentum of the dart. Okay? Doesn't make any difference. They all start the same way. Now, a lot of times, not always, one of these values could go to zero. So what do you think the initial momentum of the block is?
Zero.
Zero, because it's at rest. Okay, that's zero. I don't have to worry about that. Now, this is going to be the mass of the bullet times the velocity of the bullet. Now, I'm going to write this whole thing out. Mass of the bullet times the new velocity of the bullet plus the mass of the block times the new velocity of the block. Okay, so technically, this is the full-blown thing. But, because it's a California problem, what do you know about these velocities?
They're the same.
They're the same. You can only do this if it's a California problem. Okay, that's why I wrote this whole thing out. Don't think, oh, we can always factor out the velocity. No, you can't. You can only factor out the velocity if it is a California problem, which this is. So, what I can do over here is go, okay, this is the mass of the bullet, velocity of the bullet. And then I'm going to come over here and go, oh, this is going to be the mass of the bullet plus the mass of the block times some v prime. Okay? Now, at this point, what's the only thing you don't know?
V prime. V prime.
Of what?
The new system.
No, because Danny said everything is going to move off at 6 meters per second.
So the
I know what v prime is.
speed of the bullet.
Only thing I don't know is how fast the bullet's going.
Yeah.
Okay? That's the only thing I don't know. So, to do that, this is my unknown. So I'm going to divide everything by the mass of the bullet. Okay? Cool. Got this. So, mass of the bullet is 15 grams, which I'm going to convert into by dividing by, and I'm going to get 0.015 kilograms. Mass of the block was exactly 1 kilogram. The velocity of the system is 6 meters per second. and then I'm gonna divide by 0.015 kilogram. Now, can I just cancel these two out?
No.
Oh, absolutely not.
No.
Why?
That's not how.
Because
you have
you're not
to.
multiplying.
It's
Huh?
in a parenthesis.
Well, number one, it's in parentheses, and we're adding these, we're not multiplying. Okay? So don't get clever. Now, let's think about this. Before you do any math at all, what do you know about the sign of the velocities, of the bullet's velocity? Is it going to be a positive or negative value?
Positive.
Why?
Because the other one's zero, so it's total has to be.
Yeah, I've got to come up with a positive value. There's no negatives involved in this particular problem. And again, I don't want you to think, oh, there's never negatives in momentum. Yes, there can be negatives all the time. There's just not negatives in this particular problem yet. There will be. Is the velocity going to be bigger or smaller than 6 meters per second?
Bigger.
Bigger. Why?
The mass increased of the system.
I want the same momentum, but I have less, so therefore it has to be going faster. Okay, so somebody get out a calculator and give me an answer.
Yeah, 406.
What'd you get?
406.
406? That's not bad. A little bit faster than the speed of sound. Okay? 406 meters per second. Cool. Now, and this is actually how they test, this is how they figure velocity speeds of bullets, is that they will shoot them into an object because it's easier to measure how fast this thing is moving afterwards than trying to time the velocity of the bullet coming in. Okay, it is like, fire, boom, bam, okay? That's not very accurate. But I could have it slam into ballistics gel and stop and make that system move. Oh, I can measure that velocity. Oh, that's something I can work with. All right, now, what I want to do, I want to look at this, now that we have a bunch of numbers, now I'm going to change this system up. So now I'm going to draw a velocity time graph. Okay? So let's start with this. Is the velocity of the bullet going to change when it strikes the block?
Yes.
Because it's going to come in at,
406.
and it's going to move off with the block at
6 meters per second.
Now, I don't want you to think that the final velocity of the bullet is 0, okay? It's not, because it's moving with the block, okay? So that would be like me sitting here, Sean throws a heavyweight medicine ball, and I catch it, okay? Well, if I catch that, I'm gonna move off like this, all right? So the medicine ball is not gonna go to 0. It's gonna have the same velocity that I'm gonna have. So what that means is that if you were to look at the bullet, it's going to start up here at 406, and it's going to drop to what?
6.
All the way down to
6.
6. Okay? Boom. Now, what's the block going to do?
Travel up from 0 to 6.
It's going to go from 0 up to 6, because it's going to speed up during this time. Okay? So the block is going to go from 0 to 6. Is the time that it's going to take for the bullet to slow down equal to the time that it takes for the block to speed up? Yes, because they're interacting together, right? So the assumption that we're going to make, I don't know what this time is, we'll deal with the time later, okay? But after this happens, then this becomes a horizontal line, and they're going to move off together at 6 meters per second. So, did the block accelerate?
Yes.
Did the bullet accelerate?
Yes.
Yes. Okay. Do I have enough information to calculate the change in the momentum of the bullet?
Yes.
Do I have the mass of the bullet?
Yeah.
Do I have the initial velocity of the bullet?
Yeah.
Now, do I have the final velocity of the bullet?
Yeah.
Yes. So I can do this all day long. I can sit here and go, okay, cool. So the change in momentum of the bullet, mass times V minus V naught. So that's going to be 0.015 kilograms. The final velocity was 6. This worked out actually rather well. 406. So somebody take 6 minus 406 and multiply that by 0.015.
Syntax error.
That's always awkward. If you ever have a girlfriend that gives you that, run away.
It's -6.
Negative 6.
-6.0 Newton seconds. Cool, nice, got it. Okay? Now, did the block's momentum change?
Yes.
Yeah.
Yeah.
Did. So the change in momentum of the block is going to be its mass, which is 1 kilogram, and its final velocity was,
6.
and its initial velocity was,
0.
and its change in momentum of the block is
6 Newton seconds.
coincidence?
No.
I think not.
I think not. Why?
Because the bullet transfers its
When you add them, they should be 0.
momentum to the conservation of momentum.
Oh, conservation of momentum. When you add them together, it has to add up to the original amount.
Yeah.
So that would be like I walk in and I have 10 $1 bills. Okay, that's how much I bring into the room. I give 2 of them to Will. I give 5 of them to Danny because he's got a nice Halloween costume on. Okay, so how much do I still have?
It's 3.
3. So the same amount of money is in the room. Money has to be conserved. So there's still $10, but Will has 2 of it. Danny has
5.
5. That way he can go find a nice bride. Okay? Trying to help you out with that. Okay? Here's $5. Go find yourself a nice bride. So, but everything still has to add up to the same amount. Now, if we come up here and we say, all right, let's say, for the sake of argument, that time it took for the block to speed up and for the bullet to slow down was a half a second. At this point, could I calculate the force exerted on the block?
Yes.
By doing what?
Ft equals. That's a
Because force times time equals change in momentum, right? So change in momentum over time, which is a rate function, equals force. So for the bullet, I'm going to take -6 Newton seconds, and I'm going to divide that by a half a second. The seconds are going to cancel out. I'm going to get
12 seconds.
-12 newtons. Or seconds, whatever. Okay? Now, so that's for the bullet. What's the force on the block going to be?
12 newtons.
Positive 6 Newton seconds divided by a half a second is going to get you.
12 newtons.
Ooh, what do you notice about the forces?
They're equal and opposite.
Oh, they're equal and opposite. So you prove Newton's third law by the conservation of momentum. Okay? Because whatever momentum lost has to equal the momentum gained. Times of the interactions has to be the same, therefore the forces have to be
Equal.
equal and opposite. Okay? Now, could I calculate the acceleration of the bullet?
Yes.
Probably.
Do you know the force acting on the bullet?
Yes.
Yep.
No, it's
You know the mass of the
Yeah.
bullet.
Yes. Yeah.
I could find
Acceleration.
the acceleration of the bullet. So let's calculate the acceleration of the bullet. So somebody take -12 newtons and divide that by 0.015 kilograms.
Wait,
800, negative 800.
What'd you get?
Negative 800
-800
meters per second.
meters per second squared.
So is that under
Now, the acceleration of the
It's
block,
or act?
of the block, that's going to be pretty simple. That's just going to be 12 newtons divided by 1 kilogram, which is 12 meters per second squared. Now, this is where it all becomes one big picture. how do these numbers relate back to that velocity time graph?
The slope.
Ah, it's the slope of the line. So the slope of the bullet's line is negative 800 meters per second squared. And this one's going to be
12.
12 meters per second squared. Cool. Got it. Grant. Okay, so when you deal with momentum problems, listen to me, listen to me, listen to me. They aren't that difficult, okay? Especially relative to the calculations on gravity, okay? There's nothing cubed, squared, nothing weird. You don't have to worry about pi squared, okay? If you work pi squared into here, there's something going for you wrong, okay?
Means I won't forget the squared numbers.
But where this goes south, and again, I've been doing this for decades now, you think it's easy, and you try and take shortcuts, and you don't write stuff down, and then you get answers that make no sense, okay? So I'm just telling you, avoid the shortcut. Just keep that going. So here's the assignment. No, there's not like a backside to it. It's just this,
That seems like a
How
lot
would
of
you
fun.
say it is compared to this one in terms of time?
about the same.
You're super fun just from you.
If you did homework before like 10 p.m., then maybe you would have this.
Yeah, baby.
Oh,
Any
and
graphs we have
oh,
to
ask
draw.
about the one question.
Oh, yeah, the average force and actual force.
Yeah,
Average force is just when you draw a horizontal line on the force time graph.
yeah, but it's the one where we don't have a force time graph. It's
Yeah.
11. The soccer ball. We have a velocity time, but not a force time.
Well, but it's just force times time equals change in momentum. So
So
when
we're
we
gonna
calculate the force,
Would it be the same for both of
Because
them? The average force
is a
and
rectangle.
yeah,
Max is
average force is a rectangle. F max would be the triangle.
But it's asking for both.
I know.
So there's
Well, are they the
The
same?
areas are the same.
So it's the same.
so it's the same number.
You take that for, I'm just telling you.
Yeah.
Okay. So on this assignment, let me kind of go over a couple of these. So when you get to question number 2, it says an external force can change the momentum of an object. How can the internal force of a car's brakes bring a car to rest? So here's the deal. Let me give you a quick lesson on automotives. So when you look at, this is like the side profile of your car. There's something called the rotor, and then you have something called the caliper, which slips over the rotor. So here's your tire. So when you hit the brakes, what happens is that the caliper collapses, and it creates friction on the rotor, therefore the tire slows down. So that's the internal force, okay? But here's the question. Just because you hit the brakes, does that necessarily mean the car is going to stop?
No.
No, what else do you have to have?
Friction.
Friction, because if you're on a sheet of ice, what?
Paper filter.
Oh, that's awkward. Stapling, it's a skill. So, just because you stop the tires doesn't mean you're going to stop. What else? You also have to have friction.
Friction.
Keep that in mind when you answer number 2. When you get to question number 4, look at the visual that I just did with the different polymers. Okay? One bounced, the other one didn't. When you get to question number 10, so let me kind of give you the visual on number 10. So here's this, and I was nice, I left off friction, okay?
Yes.
So this length is 1 meter. This angle is 30 degrees. And I've given you the weight of the block, 24.5 newtons. So when you let go of it, what's the only force acting on it?
Gravity.
Well, specifically,
Force
force parallel. Okay, so you gotta go old school force parallel net force.
Oh man.
So it's gonna slide down to frictionless block, or plank. And then there's another one resting at the bottom. They're gonna come down, they're gonna hit, it's gonna turn into a California problem, and then they're gonna move off together. But as is often, so often is the time, once you move off together, now there's friction. Okay? So there's no friction, they hit, they move off together, then there's friction. Okay? When you get to number 11, you have three astronauts, Huey, Dewey, and Louie. Anybody know the reference of Huey, Dewey, and Louie?
The three
DuckTales?
students.
DuckTales, there you go. Okay? So, they're floating in
The Three
empty
Stooges.
space, and they're all at rest. Okay? So let me kind of give you this visual. Here's Huey, Dewey, and Louie. Okay? And they're just there. We don't have to worry about friction. They're in empty space. So, here's what's going to happen. So, they're at rest. Huey is at rest and pushes Dewey towards Louie. So Huey and Dewey push off of each other. Okay? Louie is not part of the story at this point. They're going to push off of each other. Okay? Then, afterwards, Dewey is going to do a stop after he pushes on Dewey. So then you're going to have this interaction. But here's the whole key to this. What's the initial momentum of the system?
0.
So afterwards, what does the momentum have to add up to?
0.
Just keep that in mind. Okay, all right. When you get to question number 12, it says on the back, this is what's on the back. Okay, so it's a multiple choice question, all right? So, and then you got the questions out of the book. So that's when it says on the back, this is what this is referring to. Okay, I'm done. You're on your own. Well,